Good morning. Today what we're going to do is a third example of related rate problems for Calculus 30. This time around we're talking about a water tank, has the shape of an inverted circular cone, a base radius of 2 meters and a height of 4 meters. It's talking about if water is being pumped into the tank at a rate of 2 cubic meters per minute. They're asking us to find the rate at which the water level is rising when the water is 3 meters deep. So to begin with, we start with where's my pen here? We start with the first step, which is talking about our diagram and a general formula. Now in this particular question, they're talking about this inverted circular cone. I'm going to go out on a limb and say that we have some kind of a cone that is shaped like this. When they talk about the information in the question, they're talking about water being pumped into the tank. So we know that we have a volume measurement of a cone. So to me, the general formula that we're going to need to focus on is the formula for volume of a cone. Pi r squared h divided by 3 is the formula for a cone. And some of these formulas we may not remember. I know this formula goes back to grade 10 math, and so it may need a little bit you may need a little refresher in terms of all of these formulas. Now, when we talk about the information in the question, we are talking about the water in the tank. And so the measurements that they gave us are not about the water in the tank. They're telling us that the radius of the tank with the base of the tank has a radius that is equal to 2 meters. The height of the tank, whoa, that's not very straight, sorry. The height is 4 meters. Now, again, that is about the tank itself. When we talk in this question, we're going to need to talk about the water level. And so when we talk about the water level, we're talking about the water level wherever it may be. So when we talk about the height and the radius of the water level, what it's going to do is it's going to resemble or be similar to the shape of the cone. And so those are some things to take into consideration as we are looking at this problem. So step number 1, we have accomplished what we need to do there. Step number 2 is talking about substituting in any constant values. In this particular question, we have to look at, is the volume going to stay constant? Is the height going to stay constant? Is the radius? None of those measurements are going to stay consistent when you take a look at this particular shape. So I would say in step number 2 that we do not have anything to do. So we've accomplished step number 1. Step number 2 doesn't have any parts to it. So we can move on to step number 3. Now, step number 3 was to take the derivative. Hang on a second, let me go back here. I got to spell derivative correctly. So our third step is to take the derivative. Now, in this particular question, there's one thing that I am going to do before I jump into taking the derivative, because when I look back at my formula, there are 2 different variables here. That means that when we talk about derivative, we would have to think about the product rule to find the derivative of these 2 variables being multiplied together. That would give me, in the end, some r values when I do not take the derivative of r squared. When I take the derivative, we'd have dr dt. We'll have some h values when we don't take the derivative of this part of the product rule, and we would have dHdt. So there's a lot of things there that we need to have information for. So for example, just to make a list, if we took the derivative now, we would have a dv dt in there, as I said, we would have an R, we would have a dr dt, we would have an H and a dH dt. And so there's a lot of unknowns in this particular question. And I'm not even sure if we have that much information in the question about the level of the water. In reality, we do have the water being pumped in at a particular rate. So we do have this measurement. We have to find the rate at which the water level is rising. So that would be a dH dt. We would have a height. We have absolutely no information given to us about the radius or the rate at which the radius is changing. So that presents a little bit of an issue that we are going to have to deal with before we get to taking the derivative. In this particular scenario, as I said, what we are going to have is the water level mimicking a similar triangle to the height and radius of the cone itself. So before we take the derivative, there's kind of an in-between step that we're going to have to do just to get our equation ready to take that derivative. And so when you compare the height and the radius, yes, we have a radius of the tank at 2 meters. The height is 4 meters. And so we will be able to say that the water level would be able to continue at this comparison where the height is double the size of the radius. And because I have so much information about height in my question and so little about the radius, I'm wanting to see if I can replace all my radius, my R values, my R variable, in our equation with h's instead. And so what I'm going to do is I'm just going to do a little quick cross multiplying here. 2h is equal to 4r. That means that wherever I have a radius, I could replace it with half the height. So what I'm actually going to do in this question, before I get to taking the derivative, I'm going to rewrite the equation with only h's in it. So I'm going to replace the radius with what it's equivalent to, a half the height. That radius was being squared before, times the h that was already there, all over 3. So I have an equation now that needs to be tidied up. In terms of my numerical values, I have the 1/2 being squared. That's going to be a 1/4. I'm going to have a pi. I'm going to have the h's. H squared times another h. I'm going to have h cubed all over 3. Now, sorry to make this messy, but what that means is essentially I'm going to have pi h cubed over 12 as a formula for this particular cone. Not every cone, but this particular cone. So now that I've taken that step of replacing the variables that I know nothing about with something equivalent, I believe now I'm ready to go on to step number 3 and take the derivative. So when I go to take the derivative, I'm working from this version of the equation. And this time around, I only have one variable, and there's no product rule here. So when I take the derivative term by term, derivative of v is 1 times dv dt. Pi over 12 is just a number that's going to be out the front. When I deal with the power, the 3 is going to come down, and the h drops its power to 2, and dh dt is going to finish off my derivative. So when it comes down to taking the derivative and substituting in the values, which is step number 4, change my color here. Step number 4 is now to substitute in specific values. So going back to my question, dV dt, I got to peek way back up here. We had a rate of 2 cubic meters per minute, 2 cubic meters per minute is the rate at which our volume is changing. Pi over 12 times the 3. Now the height at which our question was focusing on was when the water was 3 meters deep. And so I'm going to substitute in 3, and our unknown is dH dt. So I have all my information now that I've substituted in. We can, in step number 4, begin to solve for our unknown dH dt. So I forgot my unit here. I'm just going to squish it in here in meters. So what I end up having is these 2 cubic meters per minute. On this side I have a 3 and a 3 squared, so I have 9. 9 times 3, so right, I gotta go back and make that a 27 pi over 12, and we have that unit of meters squared. Seems kind of awkward there, but that's okay. And our dH dt. So solving to get dH dt by itself means I have to get rid of these numbers that are multiplied to our dH dt. And so I'm going to divide by the 27 pi on this side. I will divide by the 27 pi on this side is where our meters squared is going to go. That takes care of our unit as well. We're going to end up multiplying by 12 to cancel this 12 on both sides. So my 12 is canceled, the 27, the pi is gone, the meters squared is gone. And that means that now what's left on this side of the equation is simply our dH dt. But we've got a few numbers over here. It looks like we've got 24 over 27 pi is what we have for a numerical value, an exact value, and our units have been simplified down to meters per minute, which makes sense for how the height is changing. It is increasing at a rate of, now I'm just going to reduce my answer. Both our 24 and 27 can divide by 3. 8 over 9 pi meters per minute. And of course that is an exact value. We can always turn that into a decimal to answer our question, but ultimately we have found our solution to how the height is changing. Being that it's a positive value, I would want to say that the height is increasing at a rate of 8 over 9 pi meters per minute. So in this particular question, we have a couple of different scenarios. This scenario right here, where we are needing to change our variables so that it represents more of what we were given in the question, is something that's different. It allowed us to simplify our equation to something that had fewer variables in it that matched what we were given, and the derivative process was a little bit easier. And so if you are running into a question like this, often it is when you go to take the derivative and substitute in these specific values, that if you don't have enough information, that's kind of your clue that you may have to go back and substitute in a change of variable to something that's equivalent, so that you have less variables that match more of what was given in the question. But that is a third example of a related rate problem. Have a good day.